Okay, you know, this is interesting on the camera. When I look like this, I look like I'm looking at you, right? But when I look like this, it looks like I'm looking down, but I'm actually looking at myself. I'm looking at myself right now. I'm looking at you. I'm looking at the camera. So anyway, that's weird. And I don't know the proper use of eye contact for Zoom sort of meetings. So this is interesting. If I look at this, I can't see I can't see my screen. So even though we have better eye contact, we have a better communication. Okay, let's see. What are we going to do today? Let's talk about the exam. Anything to do with the exam? No, nothing to do. No, everybody's happy with the exam. I'm very impressed. I feel a sneeze coming on. That's the reason my hesitancy here. And it's always difficult to sneeze on a Zoom presentation. It went away. Okay, I have a challenge for you. This is very non-scientific. Who are we missing today, by the way? 1, 2, 3, 4.
Matthew.
Matthew. Okay. Hope all is okay. Okay, I was going to go down a rabbit trail. I'm not going to go down a rabbit trail. So there's no questions about the examination. You think you have your handle on all of them?
Haven't tried everything yet, but
Okay. Well, you got 2 more days, so this is the last minute, I suppose. So with that, I just spilled coffee on my smart screen here. Okay, hopefully that won't do any harm. Let's, I'm going to share my screen here. And I'm just going to ask kind of by a show of hands, how many got problem number 1? Okay.
I think I did.
You think, were you surprised by the answer?
It still doesn't make logical, or it doesn't make good gut sense to me.
It doesn't make good gut sense. Yeah, that's the reason that I gave it to you. Should you trust the math? Should you trust the science? Apparently, yes, here, because it's pretty well established, just like the Monty Hall problem. And it's very, I think it's just fascinating. And you're right, it isn't entirely intuitive. Okay, number 2. How many got number 2? Raise your hands. Okay, Justin is giving one of these. That's the
I have something that might.
What's that?
I have something that I feel like checks out, and I thought of a creative way to implement it.
Okay, that's what you need, is a creative way. What I was going to say, you know, when you're a queen and you're riding in the back of a car in a parade, what Justin did is how they teach the queens to wave. Yeah, it's turning the light bulb, turning the light bulb, turning the light bulb. That's right. That's what they do. Okay, okay, how about number 3? My gosh, guys, this is a big part of your grade. Okay.
On number 3, I saw in the notes that like where we were, we had the example of z equals x times y, and
yes,
we went through finding the PDF for z, but I didn't see in there, I guess, or maybe, I don't know, I didn't see in there where we found the CDF. So, and the way you ask it first leads me to believe that you would want to find the CDF first.
Yes, this problem, you do the CDF first, the cumulative distribution function. And so that's what I would suggest you do. And then if, for my answer in D, I got an answer with a log raised to the 2 power, log squared of something. So it's not a really pretty answer, but it's something which is tractable. I thought I'd throw you in an area of simple algebra that might mess you up. So let's see, anybody get 3A?
I have an answer.
Okay.
Based on just kind of like looking at what the possible
Yeah, that's all
sessions
you,
could be.
that's all
figured
you
it out.
have. Yeah, exactly. You look at y is equal to 0 and x is equal to 0, and then y is equal to 1, x is equal to 1. And you kind of look at the overall limits. Okay. Number 4, anybody do 4? Okay. Wow. Okay. 2 days left. You guys are last minute sort of people, right? And then anybody get 5? Okay. Well, what can I say? What can I say except to plow on and give you the grades that you deserve? By the way, everybody comes into the class with an A. You know that, right? And you have to destroy my faith in the fact that you deserve an A. So that's where we're going. That's where we're going.
I've been working through it, and I'm getting to 4.
You're getting there. Okay. Well, it looks like there's an all-nighter coming up here. Okay, let's go back now to the central limit theorem, which is one of the most wonderful results in mathematics. And the basic idea is if you convolve enough functions with each other, that you will eventually get a Gaussian under some certain conditions. Remember, the condition is that each one of the functions that you multiply, or I'm sorry, you add, if you add random variables with that distribution, each one of those distributions has to have a finite mean and a finite variance or standard deviation. So that's a criterion for the central limit theorem. We're going to use a lemma. This is a good lemma, right? And this is the limit of 1 plus beta over n is equal to e to the minus b. Now, how could you prove this to yourself? I give you the answer here. It's L'Hopital. By the way, I was just reading about L'Hopital. Do you know that L'Hopital, there is historical uncertainty whether or not he purchased this theorem from Johann Bernoulli, because he was a student of Johann Bernoulli. L'Hopital published a text in calculus, and Bernoulli came out later in his life. This is another Bernoulli, and he said, L'Hopital swiped all this from me. And L'Hopital famously offered Bernoulli money because L'Hopital was royalty, and he offered Bernoulli money to come and work with him and to be his teacher. So historically, this might be a case of big bucks, where you have big bucks in your royalty. You can buy your fame. You can buy yourself a mathematical theorem. And so L'Hopital was like that. I hope I spelled L'Hopital correctly. Do you believe this, by the way? This is a very important argument. It was one that was first, I believe, well, I don't know if it was first, but it was used by Euler. And it's, let's see, 1 minus beta to the n. Okay, so let's do this. And this is the limit, of course, as n goes to infinity. And the question is, what is it? You notice that for n is equal to infinity, for n is equal to infinity, this number becomes 1 minus 0 raised to the infinite power, right? Or equivalently 1 to the infinite power. 1 to the infinite power is a classic form of L'Hopital. We don't do this because we can't apply L'Hopital to 1 to the infinity, but we can take the log of 1 minus beta over n raised to the nth power. And this becomes then n times the log of 1 minus beta over n, 1 minus beta over n. And this is something that we can handle by L'Hopital, because what we get here is we get, if n goes to infinity, we get infinity times, and if we put n is equal to infinity here, we get the log of 1 right? If n is equal to infinity, we get the log of 1, which is 0. And so we get an unresolvable answer. So we can differentiate the two sides. And we differentiate, let's see, how should we do this? How about the log? I forget which way this goes. Let's do it this way. This is more conventionally L'Hopital, I guess, because this goes to a 0 over 0 situation, right? And if we differentiate the numerator, we get 1 over 1 minus, but we get the derivative of this, and the derivative of this looks like beta over n squared. Is that right? I think that that's right, with a minus sign. And then the denominator, we get a minus 1 over n squared. Well, this isn't working out at all, is it? Oh, no, on the top, we get 1 minus beta over n. I'm sorry. No, we don't. Come on, guys. Elementary calculus. Differentiation of the logarithm. That's, okay, let's just forget this whole thing. This thing then is over minus 1 over n squared. You can see that the n squareds eat each other up. This eats each other up. And this becomes what? 1 over, oh, I'm sorry, beta over 1 minus beta over n, right? So I'm doing some real quick calculus. This is n goes to infinity. And I forgot a minus sign here. This should be a minus. This should be a, let's see. Yeah, this should be a plus. This should be a minus. So the limit as n goes to infinity becomes a minus beta. So the log of this, what the heck was that? The log of this we know approaches minus beta as n goes to infinity. That's using L'Hopital. So therefore, 1 minus beta over n approaches as n goes to infinity, e to the minus beta as advertised, right? So that's just revisiting calculus 1. I did it very quickly. I might have made a mistake, but I'm sticking by the result. And this should be 1 minus beta over n raised to the nth power, right? Okay. And so it goes e to the minus there. E to the minus beta. Okay, what would I do? I'd have to stop sharing, and then I have to share my screen again. Okay, so this is what we just proved here, that this limit approaches e to the minus beta. And that's going to be important in our proof of the central limit theorem. The other thing we can do is we can look for small values of epsilon. And this is the Taylor series expansion for e to the epsilon for small values of e. These are for small values of e. And this is, you remember what e to the x is, right? This is something I think that I don't know, in my area, everybody should know. That's equal to the Taylor series for e to the x, and this is the Taylor series for e to the epsilon when epsilon is very small. The idea that if we added on the epsilon cubed over here, that if epsilon is small, that's going to be so close to 0 that nobody cares anymore. So this is the Taylor series expansion for e to the epsilon. Okay, here's our preliminaries. And I think I'm going to go to full screen here because I think I have some graphics in here, which make it easy. This is what we've spent some time on. We've spent some time on the sums, right? We spent a lot of time on sums, and then we spent some time on the z factor. The z is equal to s minus n bar. This is equal to what? Z bar? And this on the bottom is equal to the standard deviation of Z. I'm sorry, not, shoot. Okay, let me, I'm getting my Z's and, okay, doesn't let me erase there. What is this equal to? What should have I written there? Can anybody tell my mistake? We'll kind of play Wheel of Fortune, and I will start to write it out and see who can identify it quickly.
Would that be S bar?
Yes. Okay, good. Okay, you get a free spin. And what about this down here? It should be the standard deviation of the sum. Standard deviation of the sum. Remember, as you add these random variables, you're convolving the underlying densities so that the overall density spreads out more, and more. And the reason we do this Z transformation is because it removes from the thought process what the value of Z bar is and what the variance of Z bar is, because Z now has a mean of 0 and a variance of 1. So we don't have to worry about them because we've kind of factored them out, which is kind of cool. Okay, so we will show that the characteristic function of the expected value of e to the j omega z approaches the result which is shown here. Now, this, of course, is the characteristic function of z. So we're going to look at the characteristic function of this random variable z. And we're going to show that it approaches this result, this Gaussian. This, of course, is recognized as the characteristic function of a Gaussian probability density function. This has a corresponding density function. This has a corresponding density function of this, which is a Gaussian random variable. So if this is the probability density function, this is the corresponding characteristic function. We're going to show that as n goes to infinity, let's remember what n is. N is the number of values in the sum. So if we add these up enough, that we're going to get this result. By the way, we are assuming IID random variables here, aren't we? Because we're assuming that all of the random variables have a standard deviation of sigma and a mean of x bar. So these are indeed IID random variables. Okay, that's the Gaussian characteristic function. Here's the preliminaries, and it's not that bad. Let's look at this. The expected value of e to the j omega z, well, from the previous result, z is equal to this stuff. So it's e to the j omega, all the stuff in parentheses. And then we can write the stuff in parentheses as we do here, as the summation of k is equal to 1 to n of x sub k minus x sub bar. Now, you'll notice something interesting here. E to the summation is equal to the product of e, right? This is kind of a shorthand notation. E to the 2 plus 3 is equal to e squared plus e, or times e cubed, right? So that's what we're going to do down here. We're going to take the summation and we're going to suck it outside here. And then once we get the summation outside, we're just going to make it into a product. And this is the result that we get. We get the product of k is equal to 1 to n of e to the j omega, this stuff. Is that okay? So this is a little bit of math, but again, this is a very important theorem. So if we continue, this is copied from the last page. And since the x sub k's, these random variables up here are IID, then all of these random variables are going to be exactly, have the same density function. So in other words, the product here, the product is going to be the same thing as the expected value raised to the nth power. It's just like saying A times A times A, that's the product here, is equal to A cubed, right? This is all that we're doing here. We're doing the product of these expected values. All of these expected values are going to be exactly the same. Why are they going to be exactly the same? Because all of the x sub k's are exactly the same in terms of their describing probability density function. So if we take this product and we denote it by a raising to the nth power, we get the expected value of this thing, e to the j omega, blah, 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 raised to the nth power. Is that okay? So we go to the next result, and here we have this this result. So here's what we're going to do. See this e to the j omega? This e to the j omega, I am going to expand in a, I'm going to expand it in a Taylor series. And since the argument of that Taylor series is going to be small, I can just choose the first two elements like we showed previously. So this characteristic function, if I take the e to the j and I write out the Taylor series for it, I get 1 plus this result plus this result. And this is raised to the nth power. Again, we can avoid the cubes because what happens as n gets really big, and we're assuming n is really big to apply the central limit theorem. If you here you have 1 over the square root of n raised to the first power. Here you have 1 over square root of n raised to the second power. The next term is going to have 1 over the square root of n raised to the third power. And you can see as n goes to infinity that since this number this number is going to get closer and closer to 0, isn't it? So we can avoid this number and not even talk about it because as n goes to infinity, previous terms are totally going to swamp this term. Previous terms are totally going to swamp this term. The other thing we recognized is that the expected value, if we take the expected value of, let's do it over here. If we take the expected value of the second term here, well, the only thing that's random in there is the x bar. So this is exactly the same as sucking these constants out in front. And of course, what is this equal to? This is equal to 0. Because the expected value of x sub k is equal to x bar, because they're IID. They all have the same exact mean. So for that reason, we can totally get rid of this second term because that second term is going to be equal to 0. You with me so far? So what we're left in the Taylor series expansion is the expected value of 1, this second term goes to 0, minus this omega squared thing. And this is equal to this expected value. And let's take a look at this. We know that the expected value of x plus y, I don't know if we talked about this, but this turns out to be the case. It's the expected value of x plus the expected value of y, right? In fact, the expected value is a linear operator. And what's the expected value of 3? Expected value of 3 is 3. right? Yeah, because the expected value of a constant is a constant. So we're going to apply this here. We're going to take the expected value of 1, that's going to be 1, and then we're going to take the expected value of this second term. Now, the only thing that is stochastic in here is this xk minus x bar, and this thing, if we take the expected value of this thing squared, we get the value of sigma squared. That's exactly what sigma is equal to. And so all the expected values go away as we take the expected values, and then we have the fortuitous canceling of the sigmas here. And we are left with this omega squared over 2, and then 1 over root n squared. 1 over root n squared is 1 over n. So this becomes this, and this is this lemma that we did, right? That is, n gets really, really big, and we take the limit as n goes to infinity. We have an n down here, and we have an n up here, and as the limit as n goes to infinity, we get an e to the minus omega squared over 2. And that completes the proof. This is the characteristic function of the Gaussian, right? It's the characteristic function of the Gaussian. So we have shown that for IID random variables, if we add up enough of them, eventually we're going to asymptotically approach the e to the minus omega squared over 2. Now the problem and the question which was asked is, how big do you have to make n? And my response is, it's kind of dependent upon the random variable that you're talking about. But many well-behaved random variables will approach a Gaussian in 4 or 5 or maybe even 10 terms. It will be graphical indistinguishable. The Gaussian and the underlying probability density function will be graphically indistinguishable from each other. Okay? So we have proven the central limit theorem, one of the most important results in probability and important in terms of fundamental too. It's very fundamental. So that concludes that, I guess. Any questions on the central limit theorem?
I think you might have mentioned this last time, but should we be does this mean that we can, with good confidence, if we don't know how distributed something is, it's a good idea to just start out with a Gaussian and try to fit the data to that and see if,
yes, I mean, for a uniform random variable, for example, you get a Gaussian in, my goodness, 4 or 5 additions. You've seen our results where you take the rectangle, it becomes the triangle, it becomes the piecewise quadratic, then it becomes a piecewise cubic, and pretty soon it's going to be graphically indistinguishable from the original Gaussian. This is going to be true of most well-behaved functions. And you should be able to get the Gaussian in a few, I'm not going to give you a number, but you should be able to get the Gaussian in terms of addition of just a small number of random variables. And of course, the larger the number you have, the more assured you are that it's pretty Gaussian. So yeah, this is an asymptotic limit and does not approach the manner in which the sum approaches the Gaussian. It just says that the sum does asymptotically go to the Gaussian.
Thank you.
And I want you to know that where is this used? Say, for example, the social sciences, they go out and they do a bunch of, I don't know, polling of who people are going to vote for in the election. And they assume that each one of these samples is IID. And if they add the samples up, add the positive responses up, they're going to get something which is Gaussian. And if we use the example of going to the orchard and trying to figure out the diameter of an apple. Well, we don't know what the diameter of the apple is. If we have 1 million apples and we collect 1,000 apples and we do the summation of them, the summation of the diameters, we can assume that the summation of the diameters is what? Is Gaussian. That also means if you divide by n, if you recall with the transformation of the random variable, what happens if you divide by a number? Well, you simply scale the random variable, right? So if the sum is Gaussian, then the average is going to be Gaussian. So think of people in places like the social sciences or gathering data on people can use this sort of thing. They gather all of this data and they average it out and they says, my end random variable is Gaussian. And then all of a sudden you have a bunch of tools that you can apply to the probability density. So let's move on here. And let me give you an example of the way this is used in confidence intervals. Okay, I can't find my little cursor. I wonder if my battery in my mouse is wearing out. I think it is. So I am going to use my little pointer here. And I'm going to use my pointer to share my screen. Okay, well, this is a new world. Okay, let me give you an example of a confidence interval under the assumption of the central limit theorem. This is Leonard Maltin's rating, and this is an old example. This is an old example. I have an old version, 2001. And this rates 18,000 movies on video. Okay. So there's 18,000 movies on video. So I want to figure out how many movies that I've watched in my life that were made prior to 2018. I'd like to figure that out. So here's what I'm going to do. There's 18,000 movies. I'm going to choose 1,000 entries. So I literally did this. I went to a random page in the book. I kind of flipped through it at random. I stopped and went thunk, and then I tallied whether or not I've seen that movie before. Does that make sense? And then I closed the book and I went, loop, and then I did another one. Well, it turns out after I did that, and assuming each of my samples was IID, I saw 182 of these 1,000 movies. But I didn't sample totally because there were 18,000 movies. So I want to figure out how many movies that I've seen. Well, what I'm going to do is I'm going to look at the average. And this average is going to be a Gaussian random variable by the central limit theorem, okay? I have an average of 0.182, which is the empirical average of 182 divided by 1,000, right? That's going to be my average estimate of the probability that I've seen a movie in this book. So this means that if I take this 0.182 and I multiply it by 18,000, which is the number of movies that are in the book, it says that a point estimate is 3,276 movies that I've seen in my lifetime prior to 2018. Does that make sense? But now what I'd like to do is I'd like to do a confidence interval. And this, by the way, should probably be done on all empirical data. I think that if you do empirical data and you have the capability of putting a confidence interval, you can do it. Here's one way to do it. I want a 95% confidence interval. In other words, I want to know what number of movies that I saw less than 3. I want some sort of limit in here. Well, okay, I should have done this before. I want some sort of limit as to how many movies that I've seen. And to do this, I'm going to use that trick that I used before, in that sigma squared is equal to the probability times 1 minus the probability. If I use this as the probability up here, I get a sigma squared equal to 0.14, as you can see. And my Z, I want 95% confidence interval. So I want to put my 0.25 as twice the error function of Z. Why can I use an error function? I can use an error function because the central limit theorem is kicked in and I can assume that the results are Gaussian. So I'm going to have to do a 1.96. And I have to solve this equation. Twice the ERF of Z is equal to 0.95. Luckily, today you can do this in MATLAB. You can probably do it in Excel. And you just give this equation and it figures out what Z is. It solves this transcendental function. In the old days, you looked up a table, and here is Z 1.9, 1.96. So this table is 1.96. Gives me a value of 0.47. Okay, why is this important? Why is this important? Because twice of this is what Z is, but I want to have twice the ERF of Z is equal to 0.95. So solving for this, I get that Z is equal to 1.96, and that's the value that I want as the inverse error function, if you will. So what I'd like is sigma Z over root n, and I'd like that to be, this is the probability. This is the probability of my confidence interval. And you know what? I jumped the gun here a little bit. And we will find out where this sigma Z over root n comes from. So this is hopefully motivating the results that I'm going to give you. And it turns out my probability, instead of being 0.18, I'm 95% confidence. I'm 95% confidence that the probability lies between this point and this point. Okay. So to get the number of movies that I have, I multiply this lower probability by 18,000, multiply this by 18,000, multiply this by 18,000. Why do I want to do this? Because there's 18,000 movies in this book. And it turns out as the answer that I'm 95% confidence I've seen between 2846 movies and 3706 movies. Does that make sense? Now, some of these results were not clear, so we're going to go back now and we're going to make them clear. So here is where I got the results for the confidence intervals. We're going to do as before, do a Gaussian random variable and assume that the number Z is equal to the sum minus the average of the sum divided by the standard deviation. If they are IID, it's equal to this, as we've seen before. The mean of the sum is n times the mean of the random variable, and the variance is equal to the variance of the sum is equal to the variance of the random variable divided by n. And so if we do this, we can then take the average, which is 1 over n times the sum, right? What we've done thus far is we've just done the sum. We haven't done the 1 over average of the sum. We've just done the sum. We haven't done the average, is what I meant to say. And so therefore, Z is equal to, the new value of Z is equal to A minus X bar over sigma root n. In other words, what I've done here is I've taken, this is a new value of Z. We probably should call this Z of the average and Z of the sum. So if we take the Z of the sum and we divide it by n, if we divide it by n, S over A is the average, and nx bar over the expected value of A is equal to X bar. So this becomes the value of Z corresponding to the average if we take the sum and we divide it by n. And we are assured that, as always with a Z random variable, that it's zero mean with a unit variance. Now, there is a problem here. In order to get this confidence interval, wait, no, whoops. Okay, so we have this. And so we know that since it's Gaussian, we can use the error function. Since it's Gaussian, we can use the error function. And the probability that this value, which is zero mean unit variance, lies between minus Z and Z on the Gaussian plane is equal to twice the ERF of Z. In other words, since we have normalized it, we have normalized the random variable. We know that we have a Gaussian. We know we have a Gaussian and its zero mean and its unit variance. And we want to know the probability that the random variable lies between minus Z and Z. So this is a Gaussian random variable. If you recall, this area is equal to the ERF of Z. That area is equal to the ERF of Z. So the overall area from minus Z to Z is simply equal to twice that value. So we only need to know the ERF of Z on one side. And if you recall, we defined the ERF of Z That's how we define the ERF of Z, which is defined as this interval here. But we want from minus Z to Z, so that's twice the ERF of Z. So we have this result. We can take this probability here and we can just play around with it algebraically and solve for X bar. And that's what we're going to do, is solve for X bar. And X bar now lies between the average minus sigma Z over root N and plus this. So this just follows algebraically by solving for X bar in this inequality. So the probability remains exactly the same. So this is our estimate of the value of P, of the probability. The problem, of course, is we don't know sigma. Notice in order to do this confidence interval, we need to know sigma. And we don't know sigma in general. What to do? Well, this was solved a long time ago by William S. Gossett. I think I told you about him. He worked for the Guinness Brewing Company, and he was a mathematician, statistician, apparently, for the Guinness Brewing Company. He came up with the solution to this problem, this interval problem, and he didn't want Guinness to know that he published it, because they would say that, you know what, you're not spending your time enough thinking about beer, you're thinking about probability and stuff. So he published it under the name student T. And he defined this value T, and what the difference is between this value of T and the value of Z that we used before is we're not using sigma. This is not sigma squared. Rather, we are estimating sigma from the data. We are estimating sigma squared from the data. And this should be V squared, by the way. We're estimating the variance from the data and using that in there. What happens to the central limit theorem? I don't know, but it turns out that what Gossett showed is that this was a so-called student T with n degrees of freedom. You notice that n rears its head in here. So it is n degrees of, it's called a student T distribution. And so you can use, for smaller values of samples, you can use student T's distribution for the Gaussian. And it's exact if we don't know what sigma is. Hopefully you've had a course in elementary statistics which allowed you to show you this. This turns out to be the probability density function for the student T distribution in terms of gamma functions. Looks pretty awesome. Doesn't look anything like a Gaussian, but you have to figure this out. And again, in MATLAB and Excel, they probably have numerical values for the student T distribution. But there is no closed form solution. You must use a table or you must use a software to compute this. But here's the good news: as n goes to infinity, as the number of degrees of freedom goes to infinity, guess what the student T approaches? Because of the central limit theorem, the student T approaches a Gaussian. Everything approaches a Gaussian if you have enough summations in it. So yeah, the T approaches a Gaussian. So now let me revisit the problem that I had before that I gave prematurely. This is the Leonard Maltin thing. We got the probability of me watching a movie. If I picked a movie randomly from the book, the probability that I've watched it, according to this point estimate, is 0.182, which means that if I multiply this by 18,000, I've seen 3276 movies. I want a 95% confidence interval. I don't know what sigma is, but what I'm going to do is use that old trick for the Bernoulli random variable and assume that the sigma squared is equal to p times 1 minus p, which is 0.14. And if we look that up in the table, we find out that z is equal to 1.96. So sigma z over root n is equal to this number. Where do we get the sigma? We get the sigma from here. Where do we get the z? We get the z from this table. And where do we get the square root of n? We get the square root of n from 1,000. And it turns out if we use the inequality that we had before, we get that p lies between 0.15 and 0.20. Now, where did I get this? Where did I get this equation? This equation is up here. It's this equation. I have simply applied this equation. I've applied this equation to the Leonard Maltin problem. That's the reason that I looked at sigma z over root n. That was the important thing to calculate. Okay, so that concludes that. And I got the cart before the horse a little bit there, but hopefully things cleared up. Any questions for simple confidence intervals? Yeah, Theo.
Yeah, so just to kind of confirm, we in that we used sigma squared is approximated by p times 1 minus p from the Bernoulli random variable.
Right.
And is our justification for doing that is that we had n trials where either 1, yes, we had seen that movie, or 0, no, we hadn't? Like if we had a different sampling or a different set of data, would we be able to use that Bernoulli?
No, you could. Here's the point. Remember, the student T used the sample variance, right? What happens to the sample variance as n becomes large? Law of large numbers.
It should approach the actual variance.
It approaches the actual variance. So as n gets larger and larger, you can trust the sample variance to be closer and closer to the actual variance. So that would be a better way to approximate sigma squared, is with the sample variance. And yeah, with the Bernoulli, yeah, it's p times 1 minus p, that works. But I think in general, when you have a list of data, as we talked about, you could go down the data, you can compute the mean, then you can square all of those things, go down and compute the average of the sum of the squares, and then figure out what the sample variance is and use that. And you're going to be more and more certain as it gets larger and larger that it does approach the actual true variance. So we're mixing here the law of large numbers, where the sample variance goes to the actual variance, and we're clearly using the central limit theorem also. So you can see that these are very, very powerful tools.
Great. Thank you.
Okay, any other questions? Okay, let's see what other problems I have for you here. Okay, we have about 15 minutes remaining, and I think what I'm going to do here, let me make sure that this is right in the in the rotation. Yeah, I think it is right. Good, good, good. Okay, I did some things behind the scene and you just saw me looking around, but now we'll share this and we'll see the whole enchilada. We're going to start with some comments on stochastic processes. Now, before we have talked about individual random variables. We've talked about one random variable. We've talked about two random variables. We've talked about many random variables. Now, in a way, we have either a very, very large number of random variables, or if we model it as a continuous function, we have an infinite number of random variables. So here's an example of noise that was generated, I think, using an Excel spreadsheet. And every point is a different number. Every point is a different random variable. And so we got lots of random variables going on here. How do we treat this? How do we do some things? Well, first of all, we recognize that every point is a random variable. And the random variable is indexed by the value of time. Say we have a stochastic process. This is capital X of t. Capital X, again, is like the idea of a random variable. And at every value of t, it's a different random variable. At every value of t, it's a different random variable. So this random variable right here, this random variable has a mean. It has an X bar of 50. It has a mean. It has a variance. And it has a probability density function associated with it. So we can actually think of the probability density function of coming down here, and the probability density function, whatever it is probably going to have a mean of X bar, but it's going to have a probability density function with associated. So each one of these points has just a wealth of information associated with it, right? And the question is, how do we get our hands around this? I mean, it's just going to become very terrible. We do know that it has an expected value. Let's look at an example of expected value. Suppose that we had the following. We had a stochastic process, x of t, which is equal to a times the cosine of omega t. Now we're going to assume that both a and omega are random variables. So you pick a value of a and you pick a value of omega, and I'll give you a curve. So you pick an a from the probability density function of, this is a normal zero mean univariate random variable, and this is going to be the amplitude. So you can see the amplitude of each one of these cosines is going to be the Gaussian. So these are going to be the different instantiations of the Gaussian random variable. And then you're going to have omega, which is going to be uniform on 0 to 2 pi. And I just, for no reason, this is just an arbitrary stochastic process. And this is going to be what? This is going to be the frequency of the random variable, the radial frequency of the random variable. So you can see that the amplitudes are guided by a Gaussian, and that the angular frequencies are decided by omega. So you can see here that these sinusoids are going to have different frequencies corresponding to what the value of omega is. And so here are a few examples of samples of this stochastic process. Why is it stochastic? Because something in it is random. If you have anything random in the in an equation, and that equation gives you some sort of function, then that function is a stochastic process or a random variable. So can we can do all sorts of things here. We can compute the expected value of this. And in fact, what's the expected value of x of t?
Wouldn't it be 0, seeing as how all the sinusoids are centered?
Yep, it's going to be the expected value of the process. But because the random variables are independent of each other, we can write it as the product of two expected values. And since A is normal with a mean of 0 and a standard deviation of 1, we're assured that the expected value of A is always 0. So if we looked at the point 4 and we ask ourselves, okay, we got a random variable here and we got all of these random variables here. These are different instantiations of x of 4, right? So each one of these is a random variable. The mean of these random variables is equal to 0, which means that if you took all of these numbers, you added them up and divided by n, what should you get? Roughly 0, shouldn't you? Because these are just samples of the random variable, and we know that the expected value of x of 4 is equal to 0. And so these are just like these are samples of random variables that we have from the random variable x of 4. And if we average all of these up, we should approach 0 if we have enough of these examples. Does that make sense? The answer is yes, it does make sense. Okay, so this is the interesting thing about this. Now, each one of these random variables, by the way, has different properties. You can take these random variables here and you could construct a histogram. You could construct a histogram at this point. In other words, this value is such and such. Here are the little bins of the histogram. And so we're going to have a value here. We're going to have a value here. We're going to have, let's say, 3 values here. And we get this histogram. And if we get enough of these samples, can you see how this histogram is building up from these samples? This histogram is building up from these samples. And if we get enough of these stochastic processes, we can literally compute or estimate the probability density function underlying this random variable, which is kind of cool. Now, there is an underlying probability density function. There is an underlying cumulative probability function, and that's defined by this. It's the probability that x of t is less than or equal to x. So this is how we always take a random variable and put it into numbers by the cumulative distribution definition. Now, this is going to be a cumulative distribution. Now, the interesting thing, it's going to be a function of x, right? It's going to be a function of x. So I'm going to have a different cumulative distribution function if I choose here than if I choose here. I'm going to get a different cumulative distribution function. So it's going to be a function of time, whatever that cumulative distribution function is. So the probability that x of t is less than t is equal to f of x of t. This is the random variable. It is a function of x, but it's going to vary with time. It's going to vary with time. In other words, again, I'm going to have a different cumulative distribution function here than I do over here. So we have to explicitly put that cumulative distribution function changes with respect to time. And we get the corresponding density function at that point by differentiating the cumulative distribution function, as we do always. But one point doth not a stochastic process make. Let me look. I wanted to look at the time here, see how we're doing on time. Okay, still got about 8 minutes yet. So this is one point on a stochastic process. just 1 point on the stochastic process. Now notice this really doesn't define the stochastic process because 1 point could have an effect on another point, right? There could be relationships, and we could literally, we could take single points or we could take 2 points. If we took 2 points, and this is arbitrary, we take a point at t and a point at tau, then there's going to be 2 random variables. There's going to be the x of t and the x of tau, the statistic that comes from here and the statistic, the random variable realization that comes from here. All of a sudden now we have 2 random variables, and those 2 random variables are going to be a function of t and tau. So all of a sudden now we're already into 2-dimensional probability density functions, joint probability density functions in 2 dimensions, just with 2. And so we have this 2-dimensional probability cumulative distribution here, x1 and x2. It's going to be a function of t and tau. If you choose t and tau differently from each other, you're going to get a different 2-dimensional function. If you choose your tau over here, you're going to get a different distribution than you did if you chose your tau as chosen here. And it's the probability, just as you would expect, the probability that x of t is less than or equal to x1 and x of tau is less than or equal to x2. Again, remember with joint probability density functions, this comma is read as an and. And just like in 2-dimensional joint probability, 2-dimensional random variables, you get the probability density function by differentiating the cumulative distribution function, which is what is shown here. Now you can see we're getting pretty sloppy here, aren't we? Not sloppy, but we're getting complicated or complexicated, if you will, right? Because we just have 2 points on the stochastic process, and we're already up to 2 dimensions, and we have an infinite number of points. This is going to get really hairy. Fortunately, things simplify. We make some assumptions. So here we're going to jump to, let's see, 1, 2, 3, 4, 5 random variables. They don't even have to be in a row. Here's x of t1, t2, T3, T3 becomes before T2, doesn't matter, and T4 and T5. So now we have a 5-dimensional random variable that's going to be a function of your choice of T1, T2, T3, T4, and T5. If I choose differently here, the times at which these random variables are occurring, we're going to have a totally different statistical characterization of it. So, okay, you jump up to a 5-dimensional probability density function and a 5-dimensional cumulative distribution function, which is what this is. And if you're familiar with the notation we did for higher dimensions, this is the probability that x of t is less than or equal to x, and it's equal to this probability that we have here. And just like in the multidimensional case, we get the probability density function by differentiating the cumulative distribution function. So you see, if we try to maintain all of the information about all of the stochastic process, we're going to go crazy. Because we've only gone up to 5 of the potentially infinite number of dimensions, or at least large number of dimensions. And we don't want to go crazy. So we make some various assumptions. By the way, before we get to the various assumptions, let's talk about discrete distributions. And there's discrete distributions, and then there's, with the probability mass function of discrete distributions, the value can only take on values of m. So this is a discrete distribution. Notice the time is not discrete, but the quantization is complete. You might, for example, look at cars going this way and this way on the highway. And the cars going this way is +1. If a car goes this way, it's -1. And you keep track of all of the cars going by. And you would get a discrete random variable that's just limited to integers, right? This is different than random variables that occur in discrete time. Random variables that occur in discrete time are like this. In other words, the axis is labeled usually with integers. And could you have a random variable with discrete values that's also in discrete time? Yeah, you could. Yeah, an example of a random variable in discrete time, if I can use the same axis here, we could simply sample this axis at 1, 2, 4, 5, 6, 7. So these little dots here correspond to, if we sampled this continuous random continuous stochastic process, that would come up with a stochastic process with discrete values and discrete time. I think this is pretty straightforward. And I think what we'll do next time is we will start to simplify these ideas of stochastic processes. I get back to the idea that all of you have had systems theory, and you know, in order to have a system and to characterize a system, and you don't know anything about the system, you have to get all inputs for all outputs. That's the only way to characterize it. So what do? That's clearly something that we can't do. We need to do something to simplify it. So we make assumptions. We assume, first of all, that the system is linear. All of a sudden, the number of mappings from input to the output becomes smaller. And then we do linear time invariant assumptions. And we will find out that, well, and as you know, LTI sort of systems can be characterized by convolutions, very simple characterizations. We'll do something similar to stochastic processes. In fact, we have a time invariant idea of stochastic process. What's the idea of time invariant? Time invariant means that things don't change with respect to time, right? So if you have a resistor that stays the same resistor all the time, that's a time invariant element. If you have a resistor that changes resistance according to temperature, that's time varying, isn't it? So if you have a time invariant process, then you get lots of analytic mileage out of it. Well, it turns out there's something equivalent, as we will see, for a stochastic process. We will assume that a stochastic process, we will define what it means to be stationary. And it's kind of like time invariant, that the stochastic process does not change its character with respect to time. If you have white noise, for example, shh, I hope that comes through the microphone okay. But if you have white noise, shh, it sounds kind of the same in the beginning as it does at the end, doesn't it? The character of that stochastic process is not changing. In a way, it's time invariant, but for stochastic processes, we don't call that time invariant. We call this stationary. And I know you guys, I know Adam, for example, and Justin deal with stationary processes all the time. When you talk about the noise floor, for example, that's a stationary stochastic process. It's a process that doesn't change with respect to time. It's going to be, the stochastic process is kind of going to look the same yesterday as it does today as it will look tomorrow. So it isn't time invariant, because that's a term we use for systems, but it is stationary, and that's a term that we use for stochastic processes. And if you make assumptions like stationarity, you don't have to mess around with like 50,000 dimensional probability density functions. Things simplify. And that's what we're going to look at as we delve deeper into stochastic processes. Okay, any questions at all? Yeah, Theo.
I'm curious, would you say that almost every real process is stochastic? Like the example of the resistor, if we were to hold the voltage ideally constant and then count the electrons flowing through the resistor, there would probably be some variance.
It's a characteristic of your model. Clearly, if you want to get down to an electron counting situation, yeah, is it stationary? I don't know. But on a higher level, if you look at it, it's certainly stationary. It's kind of like Newtonian mechanics versus relativity. Do you see relativity in everyday Newtonian mechanics? If you throw a ball in the air, No, there is Newtonian, or there is relativity when you throw that ball in the air. Its consequences are very, very small. But if you throw that ball in the air and you begin to look down at the quantum level, all of a sudden it's a different model. So it's a function of the model. And one of the things as engineers we have to remember is that models are just models. And the degree that it applies to reality is dependent on our specific application and interpretation.
Got it.
So all of these equations, all of these things are models. And we use them because they work really good.
Thank you.
Any other questions? Okay, if not, thank you much.